When Galileo Galilei first aimed his simple telescope at the bright band in the sky, which we call the Milky Way, he discovered that the cloud-like structure turned out to be a gathering of an uncountable number of stars. On that day, our universe expanded exponentially. More precisely, not the universe itself, but the part of it that was known to humanity. 3 centuries later, the cosmos expanded again, this time even more significantly, as new generations of telescopes gave us the understanding that the Milky Way is not the only stellar island in the universe. Things became even more interesting when people learned about the expansion of the universe, and increasingly sophisticated telescopes revealed that its visible part spans an unfathomable 93 billion light-years and contains possibly hundreds of millions of galaxies. But what comes next? How much more of the universe is out there, and will we ever see it? Well, those interested in space know that due to the limited speed of light and the finite age of the universe, galaxies that are far enough from us won't be seen until their light reaches us. But does that mean that after a certain amount of time, photons from all the galaxies in the universe will eventually reach us, and we'll see it in all its glory? Unfortunately, that will never happen, because if we correctly understand what we are observing, the speed at which distant galaxies are receding is so great that it exceeds the speed of light. But is that even possible? Doesn't that violate one of the most famous laws of physics? Don't doubt it. This is one of the most controversial topics you can encounter in cosmology. Not even all scientists who support the so-called lambda cold dark matter model share this view, let alone the commenters on YouTube. And even among those who agree that galaxies can recede at superluminal speeds, many believe that we will never see those galaxies. But the truth is, we see them right now. So, let's figure out how far we are really looking into the universe, and try to dispel the myths about its expansion and its horizons. This video is not about whether our universe has boundaries or if it is infinite. That question remains unresolved. Even with all the technological leaps and advancements in astronomical observation, all we know is that the visible part of our universe points us to its boundlessness. The most accurate measurements of the cosmic microwave background show that the universe is flat, or simply so vast that we don't even notice its true curvature. The main idea we're interested in today is that the universe we see through our telescopes is almost certainly not all that the universe really is. The distribution of galaxies, their clusters, and superclusters is so uniform that it's easy to imagine a similar pattern extending beyond our cosmic horizon. It's as if we're sailing on a ship in the middle of the ocean, and looking around, we see the same scene everywhere, the same ocean. And even out there, beyond our horizon, we understand that there must be ocean as well. The cosmological principle states that no matter where you are in the universe, you will see the same large-scale structure. But it seems we'll never be able to verify this directly. So, astronomers simply observe what they can and draw conclusions about the nature of the universe based on this visible part. Now, it's interesting. How far can we see today, and what will we ultimately be able to see in the future? Let's start with the fact that when we talk about the observable universe, we usually refer to the particle horizon, also known as the cosmological horizon or the cosmic light horizon. This is an imaginary sphere with us at its center, defined by the speed of light and the finite age of the universe itself. In other words, it is the maximum distance from which light could have reached us since the Big Bang. Anything beyond the particle horizon is so far away that even if a beam of light had started its journey at the very moment the universe was born, almost 14 billion years ago, it still wouldn't have reached us after all that enormous span of time. Not enough time has passed for that radiation to reach the mirrors of our telescopes. The universe is still too young for that. It's no secret anymore that when we look into deep space, we're essentially looking into the past. Even the moon we see as it was just over 1.3 seconds ago, and the sun as it was 8 minutes and 20 seconds ago. So, what universe do we see at the very edge of the particle horizon? I've always been amazed that the limit of our observational capabilities lies at the very beginning of the universe's evolution. The events that began right after the Big Bang are what lie on the edge of the particle horizon. Therefore, the most distant and oldest light that could ever be seen, has already been seen by astronomers, is the light from the Big Bang itself. To be more precise, we didn't see the Big Bang as such, but rather the stage when the first atoms of the universe were formed. This happened approximately 380,000 years after the moment we call the Big Bang. Unfortunately, everything that happened before this event is hidden from our view because it's obscured by a wall of hot plasma that appeared as a result of the universe's early expansion. Any electromagnetic radiation, whether visible light, radio waves, or gamma rays, cannot penetrate this dense hot wall to show us what was happening even earlier, right up to that moment. So, no new, more powerful telescope will expand the boundaries of the observable universe, as happened in the days of Galileo or Edwin Hubble. Important, the fact that the Big Bang and the cosmic microwave background are at the edge of the particle horizon does not mean that they are still there. It's crucial to understand that this plasma has long since transformed into the matter we are accustomed to seeing relatively nearby. For example, galaxies, their clusters, and superclusters. Therefore, when we observe the cosmological horizon, we are merely seeing the most distant corners of the universe, which now look completely different. For some reason, it seems worth mentioning this. One of the strange properties of our particle horizon is, without a doubt, its size. Logic would suggest that it should be a sphere with a radius of 13.8 billion light-years, the distance light has traveled since the Big Bang. That's true, but the expansion of the universe makes its own adjustments. The objects that emitted photons to us from a distance of 13.8 billion light-years have long since moved farther away. All that glowing plasma we encounter at the edge of the particle horizon, or more precisely, what was born from that plasma, is now located approximately 46.5 billion light-years away from us. And the particle horizon itself is a sphere with a diameter of 93 billion light-years. But this doesn't mean that there's nothing beyond our horizon. It just means that the light from that distant and unknown part of the universe hasn't reached us yet. This, by the way, means that the boundary of the particle horizon is constantly expanding. As time goes on, more and more new photons from distant parts of the cosmos reach our planet, meaning we still have an ever-growing observable universe. Even during the time it takes you to like this video and write a comment, your particle horizon will have expanded, and new galaxies and events that you couldn't observe before will appear in it. But it's important to emphasize that the particle horizon is about the past. That is, the greatest distance from which we can receive information about the past. But what about the present universe and its future? How far can information be sent now, or from where can it be received? To understand this, we first need to talk about the Hubble sphere, our next cosmic horizon, beyond which the universe becomes very strange. The expansion of the universe, as a phenomenon, was first predicted mathematically. In 1922, Alexander Friedmann showed that the solution to Einstein's equation doesn't necessarily imply a static universe. Rather, it could either be expanding or contracting. Most scientists agreed with this view, but no one knew what the universe was actually like, because measuring the exact spectra of distant galaxies and their distances was required. Even today, this is a complex task, and back then, it was even more so. Nevertheless, by the late 1920s, this was achieved when Georges Lemaitre, followed 2 years later by Edwin Hubble, were able to determine the rate at which distant galaxies were receding from us. Hubble used a more accurate method by measuring the distances to Cepheid variable stars based on their brightness, and in doing so, he observed that the farther away a galaxy was from us, the faster it was receding. In 1929, Hubble and his colleague Milton Humason, using their observations, attempted to calculate the mathematical relationship between the distance to a star and the speed at which it was moving away from Earth. Thus, the Hubble-Lemaitre law was born, along with the so-called Hubble constant, one of the most important cosmological parameters, as it tells us how quickly the universe is expanding. The initial value that Hubble and Humason arrived at was around 500 kilometers per second per megaparsec. But this estimate was far from the modern value. Even today, no one can tell you the exact value of the Hubble parameter, as different methods of determining it yield somewhat different results, meaning scientists still have some way to go before arriving at a consistent figure. However, this parameter is generally thought to be around 70 kilometers per second per megaparsec. What does this mean in practice? It means that any galaxy located 1 megaparsec away from us, over 3 million light-years, is receding at a speed of 70 kilometers per second, and a galaxy 2 megaparsecs away is receding at a speed of 140 kilometers per second, and so on. Now this raises an interesting question. If the farther a galaxy is, the faster it's receding from us, is there a limit to this speed? Or can some galaxies move away from us at the speed of light or even faster? Well, this is precisely what the Hubble sphere tells us. If we assume that the Hubble-Lemaitre law applies to the entire universe, then at a distance of more than 14 billion light-years, a galaxy would already be receding at a speed exceeding 300,000 kilometers per second. In other words, faster than the speed of light. Yes, I agree that this is a difficult concept to grasp, but let's try to break it down. The thing is, Albert Einstein, who gave us our modern understanding of the universe on the macroscopic level and beyond, actually did so using two theories: the special theory of relativity and the general theory of relativity. The special theory describes how the laws of physics work the same for everyone, everywhere and at all times, regardless of what those people are doing, whether they are sitting at a dining table or flying in a supersonic jet. In both cases, the laws of physics affect them in the same way, including the speed of light. In other words, if both the pilot and the person at the table measure the speed of light, they will find it to be the same. If this weren't true, then our pilot, if they could accelerate to the speed of light, could seemingly catch up to a photon and see it standing still. But could that really happen? If light appeared to have zero speed to the pilot, this would mean that the laws of electromagnetism depend on the observer, the pilot. Einstein understood that this couldn't be the case, as even classical physics postulated that its laws are the same for everyone, everywhere, and at all times. And experiments with light, the most famous of which is the Michelson-Morley experiment, showed that the speed of light does not change with the observer's speed. So, in the pilot's frame of reference, in the airplane moving at the speed of light, they would still measure the speed of light to be 300,000 kilometers per second. Moreover, even if the pilot turns on a flashlight and moves toward a stationary person, the speed of light measured by that person will still be 300,000 kilometers per second, not the speed of the plane plus the speed of light, as logic might suggest. To make the speed of light constant, Einstein simply replaced absolute space and time with ones that could change depending on the observer. In other words, space-time changes for a moving body according to its speed, as seen by an external observer. This is where all those strange paradoxes come from, which sometimes contradict our intuition, especially regarding time, which flows differently for moving and stationary objects. These effects, of course, are noticeable at high speeds, close to the speed of light. But to emphasize again, these effects appear when an observer looks at a moving body. The moving body itself, whether in a train or a spaceship, never experiences changes in its own frame of reference, even if it's moving at the speed of light. In other words, it's important to always remember that when we say nothing moves faster than light, we are referring to the motion of one object through space relative to another, or relative to space itself. Now, along with quantum mechanics, the special theory of relativity is indeed one of the greatest theories in history describing our universe. But it has one significant flaw that cannot be ignored. It does not account for gravity. The special theory of relativity only works in flat, static space, which, as we know today from observations, is not the case. But even before we saw this through telescopes, Einstein understood it, and finally decided to account for gravity, expanding the special theory by proposing the general theory of relativity. It is the general theory that describes how mass can bend the fabric of space-time, and thus how it affects the universe as a whole. The key idea is that in an expanding universe, distant galaxies are not escaping by moving relative to each other within a single frame of reference. No, space itself is expanding, creating the effect of motion, even though this is not the case. The galaxies remain in their respective frames of reference, moving as they do within their clusters, and observers in these galaxies continue to measure the same speed of light. Meanwhile, the space between them and us increases. This is the key difference between the special and general theories of relativity. The special theory simply does not fit to describe this event. its equations don't align with observations. On the scale of the entire universe where expansion dominates, the general theory of relativity is needed. The redshift of distant galaxies indeed increases with distance. But this happens not because the galaxies are moving away from us, but because the space between us is expanding. This in no way violates the special theory of relativity, since that theory concerns motion. But the galaxies are not moving relative to each other, nor relative to space. This is the key point. Yes, of course, they have some movement within their clusters, and that's fine, but the main thing is that the clusters are receding from us due to the expansion of space. There is no contradiction with the special theory of relativity. So, I hope this time we finally clarified the concept of the galaxy's recession velocities and that there's no need to worry about the speed of light in this case. Now let's return to our cosmic horizons, specifically to the Hubble sphere, which, by the way, is not a horizon in the usual sense. It is simply an imaginary sphere with its center on Earth and a radius of about 14 billion light-years. Inside it, all objects are receding from us at subluminal speeds, while objects beyond the sphere are receding at superluminal speeds. But what does this mean for us? Does it mean the light from these galaxies will never reach our telescopes? Well, that's yet another widespread misconception that is often found on the internet. Even looking at our infographic, you can understand that the Hubble sphere lies within the particle horizon, meaning that objects in this area are indeed observable. For instance, the most distant known galaxy captured by the James Webb Telescope is JA-DES-GSZ 140, which has a redshift of 14.3. This means that its actual distance from us is more than 33 billion light-years, far beyond the Hubble sphere. It is receding from us at more than twice the speed of light, 2.3 times faster. But that didn't stop the James Webb from capturing it, right? Another example is a whole galaxy cluster with a long name to pronounce. It has a redshift of only 2.506, meaning it's much closer than the previous galaxy. However, its actual distance is now approximately 19.4 billion light-years, and it is receding from us at a speed 34% faster than the speed of light. In fact, all galaxies with a redshift higher than 1.45 are receding from us at superluminal speeds, meaning that the vast majority of galaxies we observe are receding from us faster than light. But how then can we see them? It's logical to think that a photon emitted by the galaxy toward us simply wouldn't be able to reach us, as its speed wouldn't outpace the space that is expanding faster than light. That is, although this photon is indeed moving toward us at the maximum possible speed relative to its local space, the problem is that its local space is receding from us faster than light. So, it seems that all those galaxies beyond the Hubble sphere should be inaccessible to us. But there's a catch. The Hubble sphere is not static, it changes its size, or more precisely, it increases. And as it grows, it can catch up with the same photon from a distant galaxy, allowing the galaxy to enter our field of view. The reason the Hubble sphere behaves so strangely lies in the fact that the Hubble constant is not really a constant, it changes over time. To be precise, what is called the Hubble constant is actually the value of the Hubble parameter at this moment in time. The parameter itself changes over time. There are different cosmological models, but most agree that the Hubble parameter changes. In other words, the expansion rate changes. And interestingly, according to the most accepted model today, the lambda CDM model, which includes dark energy, the Hubble parameter is actually decreasing. Let me rephrase that. In an accelerating universe, the recession velocity of galaxies is currently decreasing. This sounds very strange, I agree. The concept of the expanding universe truly breaks the mind. Mine has gone through it several times while preparing for this video. As you can see from this diagram, the recession velocity of the most distant galaxies is described not by a straight line, but rather by a curve. That is, the speed is actually declining. But why? Well, I must admit, I don't have a more or less reliable explanation for you. But if you believe Ethan Siegel, a cosmologist writing for Forbes, it's related to the changing density of matter and radiation in the universe, but on the other hand, the constant density of dark energy. In short, the expansion rate depends on the energy density in the universe, which tries to compress it back into a singularity. At different stages of the universe's evolution, its expansion rate should have varied. There was a period when radiation dominated the universe, and the expansion rate was high. Then there was a period when matter appeared and dominated for a while, determining the expansion rate. But at some point, no one knows why or under what circumstances, dark energy began to dominate, and now the recession velocity of galaxies depends on it. Whatever this thing is, apart from acting like anti-gravity, it also has a constant density, meaning it doesn't depend on how much the universe expands. Even if it becomes 1,000,000 times larger than it is now, the density of dark energy will not decrease, unlike matter and radiation. So, one day in the distant future, the universe will expand to the point where matter and radiation will no longer have any influence on it. But the density of dark energy will remain. Its role will be to simply continue the expansion and prevent the Hubble parameter from dropping to zero. Even when the density of ordinary matter and radiation falls to a minimum, all that will remain is the density of dark energy, which will not decrease, and thus the expansion will continue. At that point, the Hubble parameter will truly become a constant. So, even though the accelerated expansion of the universe isn't fast enough to cause the Hubble sphere to shrink, it is currently fast enough to stop the Hubble sphere from growing. So, if we assume that the Hubble sphere is indeed expanding, the photons that previously couldn't reach us will eventually make their way to us. They will enter our Hubble sphere after some time, and thus will become part of our sky. This has already happened with galaxies currently located beyond the Hubble sphere. In this way, more and more cosmic events and galaxies will come into our view, at least for a certain period. You might say, okay, that sounds cool, but shouldn't it be the other way around? Shouldn't galaxies, as they move further away from us, eventually leave our field of view forever? Isn't it true that in the distant future, we won't see anything through even the most powerful telescope, except for the stars of the local group of galaxies? Well, this is where we need to mention another cosmic horizon, called the event horizon. Yes, it doesn't just relate to black holes. In fact, this is the most important horizon in the context of our ability to communicate with the distant cosmos. It's not difficult to understand. The event horizon is the maximum distance from which light emitted now will reach us sometime in the future. In other words, it is the farthest distance from which light will still manage to cross the Hubble sphere and reach us. If an object is located closer than the event horizon, its photons will eventually become visible to us. However, if the object lies beyond the event horizon, it is so far away that the light it is emitting right now, at this very moment, will never reach us in the future. The event horizon is located near objects that are about 16 billion light-years away. All the objects we currently observe beyond this horizon are seen as they were in the past, but the light they are emitting right now will never reach us, even with the expansion of the Hubble sphere. We won't be able to send signals to those galaxies, nor receive any in return. We will never meet or communicate with potential civilizations beyond the event horizon, just as no information from beyond a black hole's event horizon can reach us. So, how will the cosmic event horizon behave in the future? It will continue to expand as long as the Hubble parameter keeps decreasing. But once the density of matter and radiation becomes too low to affect the expansion, the event horizon will finally stop at a fixed distance of about 18 billion light-years, as shown on this diagram. At that point, the Hubble sphere will lose its significance, as it will match the event horizon. In other words, any event or matter receding from us faster than the speed of light will no longer be accessible to us. Meanwhile, the expansion will continue, and galaxies will keep moving away from each other, gradually crossing beyond our cosmic horizon. At some distant time in the future, almost all galaxies around us will have left the event horizon. This means that the only galaxies with which we will still be able to communicate will be our local group. Moreover, despite the fact that the particle horizon will continue to expand, this doesn't mean we will see more of the universe in the distant future. Quite the opposite. The thing is, due to expansion, the photons reaching us will stretch their wavelength. Over time, they will be stretched so much that we won't even be able to detect them. Lawrence Krauss, a well-known theoretical physicist, claims that in 100 billion years, the redshift of galaxies will be so large that the wavelength of their radiation will exceed the size of the cosmic event horizon. Naturally, no one will be able to detect them anymore. Even the cosmic microwave background radiation will no longer be accessible to us. Thus, astronomers of the future will not be able to observe it, just as they won't detect any galaxies except those in the local group, which by that time might have merged into one supergalaxy. They will never learn about the existence of the rest of the universe, will not be able to measure the recession velocities of galaxies, and won't even know that the universe is expanding or how it behaved in the past. In other words, in the distant future, all we will be left with is our local group of galaxies, which will serve as our entire observable universe.